Hey guys, Mrs. Dan's here. So today we're going to be looking at a sequence of numbers. And with that sequence of numbers, we're actually going to be able to maybe use an equation that helps us find the next number in the sequence. We're actually going to be able to write that equation ourselves if we're given a sequence of numbers. So this sequence of numbers is actually called an arithmetic sequence. We've seen sequences of numbers before. Even in elementary school, they would give you a list of numbers and ask you to follow the pattern and find the next number. So just know that this is something that you can do, something you've done in the past. It's just that we're kind of bringing it up a level by using some notation that represents sequences. So the do now is fairly straightforward. We have to, in number one, evaluate f of x, which is defined as doing 2 times the input. So if I want to find f of 1, I want to do 2 times 1 to get 2, 2 times 2 to get 4, 2 times 3 gives me 6, 2 times 4 gives me 8, and 2 times 5 gives me 10. So guess what? I pretty much just did everything that that objective said. This here is a formula. We actually call it an explicit formula. And if I input numbers in order to find the first number in a sequence, I would plug in a 1 and I got out a 2. To find the second number in a sequence, I'd plug in a 2 and I got 4. The third number I got 6. The fourth number I got 8. And the fifth number I got 10. This sequence will continue. So this do now really does just teach everything that I need you to know. If you know about functions, you actually already know this whole lesson. So using this function, I'm now going to call it an explicit formula. I plug numbers in to find a sequence of numbers. The first number, second number, third number, fourth number, and fifth number. If I wanted to know the sixth number in the sequence, I could plug it into the formula. I'm hoping, though, that you can actually find the sixth number by looking at the pattern of these numbers. Do you agree that it looks like it just keeps on adding on 2? So you already know that the next number is really a 12, right? And the next number after that is a 14. And this pattern of numbers actually will go forever. So it really is just a list of numbers and you're looking for a pattern. When we find that number that you can add on, when we use that pattern, in this case we were adding on 2 each time, that number that we add on, we actually call the common difference. Common difference. To be honest with you, it's kind of like a rate of change, right? It's like a constant rate of change, like what we've been talking about these last couple of days with our linear functions. If the rate of change is constant, we said it was linear, this rate of change is constant. I keep on adding on 2 to get to the next number in the sequence. But instead of calling it a constant rate of change, they're calling it a common difference. Let's look at number 2. If I plug in a 1, 1 minus 3 gives me a negative 2 as an answer. When I plug in a 2, I get a negative 1. When I plug in a 3, I get 0. When I plug in a 4, I get 1. And when I plug in a 5, I get 2. So my first number in the sequence is negative 2. My second number in the sequence is negative 1. My third number in the sequence is 0. I'm really exaggerating this, calling it the first number, the second number, and the third number, because there's some notation I want you to get used to. To call something a first number in a sequence, a lot of times we like to say a sub 1. A is standing for like sequence notation. Remember we learned this function notation? Now we have like a sequence notation. So a sub 1 means first number in the sequence. A sub 2 means the second number in a sequence. A sub 3 is the third number in a sequence. A sub 4 is the fourth number in a sequence. And A sub 5 is the fifth number in a sequence. I am saying sub. It's a subscript. So we write that number really low down in the right-hand corner. First number in the sequence was -2. To get to -1, do you agree that we're adding on 1? To get to the next number, we're adding on 1. To get to the next number, adding on 1. To get to the next number, adding on 1. Oh yeah, what is that number that we add on called again? Right, it's called the common difference. So in this case, the common difference is 1. Now we actually abbreviate this common difference. We use a D to represent it. So when you look at a list of numbers, I want you to look and see if we can add on the same number again and again and again and again. If we can, we call it an arithmetic sequence. When you find that number that you keep on adding on, we call it the common difference. And this is what a lot of this says here. So an arithmetic sequence is an ordered list of numbers, right? And we're going to add a constant, and that constant is called the common difference. The formula that we use, I told you, is called an explicit formula. And we can substitute in any term number. Did you hear just what I said? I called it a term number. Let's go look at this do now again for a second. When I called this the first number in the sequence, it's the first term. And this is the second term and the third term, and so on. And remember, those terms have special notation goes with it. I like to say this is a sub 1 and a sub 2 and a sub 3 and so on. So the hard part about today, if anything's hard, is like the new vocabulary and the new notation that we're using. So it's called an arithmetic sequence. It has a common difference. If we use a formula to find that sequence, it's called an explicit formula. Each number in the sequence is called a term, and everything has a term number because these numbers are in order. So sequences really are functions, and the key really is that the input is the numbers placed in line. I think this is probably like the most important thing that you should maybe revisit very often if you're getting confused with your sequences. A sequence is supposed to be super simple. It really is just a list of numbers, and the numbers placed in line is actually what we call the term. And you can see it in this chart down here, right? If you're given this sequence, 2, 5, 8, 11, right? It's a list of numbers. Looks like I keep on adding on 3 to get to the next number. The term 2, it's first in line, so that's why we call it a sub 1. Term 5 is second in line. That's why we call it a sub 2. Term 8 is third in line, and that's why we call it a sub 3. Term 11 is fourth in line, so we call it a sub 4, and so on. Now, I've been using this subscript notation because that's what I like to use when we're talking about sequences, but we can use function notation as well. So let's take a look. So here we have a sequence. And we're going to be able to read the notation that we just learned. This is asking me for the third number in the sequence. So that would be 16. This is asking me for the first number in the sequence, and they want me to add it to the seventh number in the sequence. 1, 2, 3, 4, 5, 6, 7. Oh, add it on to 256. So it turns out to be 260. Here's notation written with subscripts. They want the second term, so that would be an 8. Be careful on D. Remember, parentheses are important. Do what's in the parentheses first. They want to know the first term. That's a 4. And then they want me to square it to get 16. The fifth term, 1, 2, 3, 4, 5, 64. Take away the fourth term, which is 32. 64 minus 32 is 32. And now, be careful, they're asking me for the input. Which input gives me an output of 128? Or, since we're talking about a sequence of numbers, what place in line is the term 128? 1, 2, 3, 4, 5, 6. N would be 6 because 128 is the sixth number in line. Again, the key. The input is simply the numbers placed in line. Let's take a look at exercise 2. So they give me a formula. I'm hoping this already is looking kind of familiar. It reminds me of y equals mx plus b. Doesn't it look like that? Right? So my rate of change or my slope is 2. My y-intercept is 1. Interesting. But let's answer part A. It says write out the first 5 elements of this sequence. So to find the first term, remember you want to plug in a 1. So if I do 2 times 1 plus 1, 2 plus 1 is 3. I think my first number or my first term in the sequence is a 3. Let's find the second term by plugging in a 2. So I have to do 2 times 2 plus 1. 4 plus 1 is 5. So I think the first term is a 3. I think the second term is a 5. Let's find the third term. Plug in a 3 to find the third term. 2 times 3 plus 1, 6 plus 1 is 7. Let's find the fourth term by plugging in a 4. 2 times 4 plus 1, 8 plus 1 is 9. And let's find the fifth term. We can plug in a 5, but freeze for a moment. Let's stop plugging in. Remember we said that a sequence really has some kind of order to it. Do you agree? We keep on adding on 2. Do I really have to plug in again? Or do you know that this is an 11? So we had to plug in to find the first one, right? I didn't know where to start. I didn't know what the first term in the sequence was. And maybe I needed to plug in the second one because I didn't know what to keep on adding on. But once I find my first term and my second term, I can now see that the common difference, which remember we can use a D to represent, the common difference is a 2. Once I learn that the common difference is a 2, why don't I just use the common difference to find the third term and the fourth term and the fifth term? So that really is allowed. You can use the formula, and then once you find the pattern, you can continue with the pattern. It says graph the sequence on the grid shown, and this is really important. They want me to graph from when n was 1 to when n is 5. So this first term, remember I plugged in a 1. This is where n is 1. So if down here are my n's, and along my y-axis are my outputs, I can say when I plug in a 1, I got out a 3. So I just plotted that my first term is 3. My second term is 5. My third term was 7. My fourth term was 9. And my fifth term was 11. I'm not going to connect these. So with linear equations, we always connected with a straight line. But since this is a sequence of numbers, and there's a first term, a second term, a third term, it really is the numbers placed in line. There's nothing in between those terms. There is no term, 1.5. This is not like Hogwarts and we have to get on platform 9 3/4, right? There is no in between of our platforms. There is no in between of our terms. So I'm not going to connect it. They're individual points. But from those individual points, I can actually see that there is like a slope, right? Or that rate of change. I can see I'm going up 2 over 1, up 2 over 1. Aren't I increasing by 2 to get to the next term? Wasn't my common difference a 2 to get to my next term? So really, an arithmetic sequence is a linear function. So that's how come this looks like y equals mx plus b. It's just that we don't connect it with a line because there is nothing in between. And our first term is not on the y-intercept. Do you see, if I were to graph my y-intercept, it would be at 1. But I don't see a number here at 1 on my y-axis. I could imagine it being there and go up 2 over 1 and I get to every point. But there is no term 0, right? If I were to line things up and I were to tell you like your place in line, if I took 5 of you and put you in a line, one of you would be first and someone would be second, third, fourth, fifth. No one would be 0 in line, right? We don't have a 0 in line. So even though it looks like a linear function, I don't see the y-intercept because there is no 0 place in line. I start with the first place in line. And I talked about why we shouldn't connect it. And it's asking me for the 21st term in the sequence. So after this 11 comes 13 and then 15, and I could keep on adding on till I get to the 21st number in line, but that's kind of lengthy. So that's how come it's nice to use this explicit formula that was given to us. Because if I want to know the 21st number in a sequence, plug a 21 in place of n. To find the 21st number in line, I'm going to do 2 times 21 plus 1. The 21st number in line is 43. Okay, so hopefully you're hanging in there with me. Some people like to kind of represent our sequences as a general formula. We've really kind of been focusing on this all unit. This is in the form of y equals mx plus b. This is the form that this explicit formula was in. Sometimes it's in another form like this, but I'm not going to focus on this right now. Okay, we're really going to focus on this y equals mx plus b. Look at this right here. Remember, this is sequence notation where we have these subscripts, and they're talking about a sub 0. They're actually talking about the 0 place in line. So we can talk about a 0 place in line even though we don't necessarily write the 0 place in line, right? A sub 1 means the first term, so a sub 0 would mean the 0 term, which really means the y-intercept, which is what we said we don't really plot here. We don't really write it here in our sequence, but we could imagine it being there. Let's go on and practice instead of focusing on this formula, because I think you can do this stuff. I think you can determine if a sequence is arithmetic. Arithmetic really means that you add on the same number again and again and again. There are lots of different kinds of sequences. There's a sequence we're going to learn later in the year called a geometric sequence, which means you multiply by the same number again and again and again. So lots of these things are sequences, but maybe it's not arithmetic. So you just have to look at, can I constantly add on the same number here? I hope you said yes, right? Can't I keep on adding on a negative 3? Right? If I keep on adding on negative 3, I get to the next number in line. So it is arithmetic. And the common difference we call D is negative 3. It says write the explicit formula. So we're going to be really careful here. We're going to kind of use this y equals mx plus b form. So we're going to imagine what our 0 term is. So if I write it in y equals mx plus b form, and in sequence notation we say a sub n equals the common difference times a number that we call n instead of x, and then we add on that 0 term. So we kept on adding on 3, so that's our common difference, or our rate of change, negative 3, I'm sorry. And the 0 term, well, comes like before 35. You're right, 38. Now, if you're not sure if you wrote a good formula, we can use our graphing calculators to test it out. Take a look at this. So on your graphing calculator, you know that we can enter things into that y equals button. So I know that this doesn't say y equals, but I keep on telling you it is like y equals, right? So in our y equals button, let's enter this equation that I just wrote. Negative 3n, remember to use the negative button, not the minus button. And on our calculator, we have to use an x instead of an n, and then add on 38. Now, how does this help me see if I wrote a correct explicit formula? Well, let's go look at our table of values. Remember, to get to the table, it's the second and then the graph button. And think about this x column here is telling you first number in line, second number in line, third number in line. So when x is 1, it tells me my first number in line should be a 35. And that first number here was a 35, right? The second number should be a 32. It is. And then the next number should be 29. It is. The next number should be 26. It is. So since my graphing calculator is showing the same list of numbers as what was here on my paper, I know that I wrote a correct formula. Pretty cool, right? It's showing me what my 0 term is. It's 38. But remember, we kind of talk about a zero term, but we don't necessarily write a zero term, because when we write numbers in order, there's a first number, a second number, a third number, and so on. So we're going to keep on checking ourselves with our graphing calculator, just so that you get used to using the graphing calculator and writing your explicit formula. So is this arithmetic? Are we adding on the same number again, 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 and again? Looks like I can keep on subtracting 20 or adding on a negative 20 to get to the next number. So this is arithmetic. The common difference is negative 20. So let's try and write the equation. Think about y equals, listen to the words I'm saying, but look at what I'm writing, right? Because I'm trying to do sequence notation, but I'm thinking about y equals mx plus b. Y equals mx plus, ooh, I need my zero term, right? I need the y-intercept. What comes before that negative 3? Yes, it's a 17. Let's go look at our graphing calculator to see if we really did it right. If we go to the y equals button, I'll type in negative 20x plus 17, and I'll go look at my table and hope that I get the same sequence. My first term is a 3. My second term is a 20, negative 23, negative 43, negative 63. I did it. I did a good job. So if we look at number 3 is not arithmetic. It is a sequence of numbers. I can figure out the next number, can't you? Aren't we multiplying by 2 each time, right? But since we're multiplying by 2, it's not called arithmetic. So we're not going to write any kind of equation for it. We're done, right? So we had to determine if it was arithmetic or not. If it was arithmetic, we write down a common difference, because a common difference helps me write the equation that goes with it. Is number 4 arithmetic? It is. The common difference is negative 10. Right? Is number 5 arithmetic? It is, because the common difference is negative 2. Is number 6 arithmetic? It's not, right? You don't keep on adding on the same number. Let's just take a look at this. They're giving us the formula, and we're going to find the first 5 terms, and we're going to find the term that they're naming. So remember, to find the first term, you plug in a 1. So negative 11 plus 7 times 1 is negative 11 plus 7, which is negative 4. So the first term is a negative 4. The second term, you plug in a 2. So negative 11 plus 7 times 2 is negative 11 plus 14, which is positive, sorry. Positive 3. So now I can see that the common difference is 7. I have to tell you, I knew that to begin with, because remember, the common difference is always in front of the n. Also, something I know that I can do is pick up my graphing calculator and in my y equals button, I can put this formula that they gave me, negative 11 plus 7x, and go look at my table of values. And I can just copy the sequence. The first term is negative 4. right? You have to look at when x is 1 to know the first term. The next one is 3, then 10, then 17, then 24. And now I just listed all the numbers. They want me to find a sub 34. That's the 34th number in line. Why don't you just scroll down to the um, 34th number here. Now sometimes scrolling a lot on your calculator takes time. Maybe it would be easier just to plug that number in, but I want to tell you that you could do this, right? When x is 34, I get a 227. So you can use your calculator to help you do this stuff. If we were to look at things like 11, 12, 13, and 14, I want to tell you that they're giving you the first term. The first number in line is a 28. And now they're giving me my common difference. So they're telling me to add on 10 each time. So the next one must be a 38, and then a 48, and then a 58, and then a 68. Given the first term and the common difference, find the first 5 terms. I did 1, 2, 3, 4, 5. And they want the formula. So fine, we'll write it in y equals mx plus b form, but we'll use sequence notation. A sub n equals the common difference times n plus the 0 term. So when I do that 0 term, I do just back it up a little bit. What would have been before the 28 if there was a 0 place in line? Sure, it would have been an 18. And again, you can test yourself on your calculator, but I know I'm right. I don't need to go look at my calculator. So I'm hoping this is feeling okay. I'm hoping you realize that it's just a list of numbers that we keep on adding on the same number again and again. You can start your homework if there's time left in class. The textbook page is attached in your Google Classroom, and it's really what we just did here in class. So I will talk to you soon. I'll be able to answer any questions you have, and I hope you have a good day. See ya. Bye.